So Namaste, this is Sunil from Hindran Engineering. Today we are at Ramakrishna Yoga Ashrama. This is located outskirts of Bangalore on the banks of pristine Bhimankuppe Lake. Here we have done a lot of decentralized energy and water management projects. So when we talk about decentralization, it is the easiest way to be sustainable. Rather, I would say decentralization is the first and the most important step towards decarbonization. So when we generate our own energy, use it, store it in the battery, and use it when there is no sunshine, we are by and large self-sufficient in terms of our energy requirement. So this gives us complete control over both the quality and the quantity of energy or the power. So in this ashram or in this place, we have got three independent systems. So we are at the main temple, the Sanctorum, and we have a student home in the campus, and we have a Cowshed or a Goshala. In these three buildings, we have got three separate solar PV systems. Each one is a battery-based system. So we are generating the energy, we are consuming it, we are storing it, and we are also using it when there is no sunshine. So all of them are like hybrid kind of solar PV system. That is, when this excess energy, it also goes back to the power utility grid. We also have a biogas plant here, which generates enough fuel for cooking purposes. This campus is spread over approximately 4 acres, and about 40 students stay in this campus, and there are about 5 or 6 support staff. So there's good amount of energy requirement for cooking, and you can see there's a large farm also. There's a lot of requirement for fertilizers or manure. So the biogas plant produces the required amount of fertilizer as well. So now I will take you to all the three or rather the 4 projects. All of them are energy storage systems. All of them are solar PV systems. So this is the main Sanctorum, or this is the main temple. Here we have got one setup. We have another setup in the student home. Then there's one more setup at the Goshala, and you saw the biogas plant. I'm going to take you to all these 3 plants, explain the technical details of these plants, and show you the energy storage system as well. So we'll start with this place. This is the main temple or the Sanctorum, what they call. So here, this house is the Mandir. It has the monks' quarters. It has the kitchen. It has a dining hall. It has the administrative office, and it also has a small storeroom. So this building, we have a solar PV plant, a 4.8 kilowatt solar PV system. This generates enough energy for this building. And another reason why we have chosen to be off the grid or be hybrid is this is at the far end of our transformer line. So there's plenty of fluctuations, lot of power cuts, very unreliable quality of power. So having an energy storage system gives us that flexibility, and it gives us we are by and large insulated from any kind of grid fluctuations or power cuts. So now this ashram and the student home is like completely powered by solar. There's uninterrupted and good quality of power supply. So I'm going to take you to each one of these units and explain the details of them. Okay, so now we will go up on this mandir and see the first power plant. So now we have come to the first setup. This is the main temple, the Sanctorum, what they call, and this is where the meditation and all the other activities of the ashram happens here. So here we have one set of PV panels. This is a 4.8 kilowatt AC coupled hybrid PV system to be called technically. So we have got 4 plus 4, 8 panels. These are connected to the micro inverters. What I'm showing you is a micro inverter. This is currently the latest series of IQ8P micro inverters available in India now. So I have explained about micro inverters, and I have spoken about the advantages of the micro inverters. There is a video, the link is given in the description. I'm going to briefly tell once more. So essentially these are like 8 panels. So 8 panels have 8 inverters. So there are 8 independent discrete system. Each panel is independent of the other system. That's the advantage of the microinverter configuration, and it's very safe system. There's hardly any DC wiring. So it's all AC configuration that makes the system very, very safe. And say after a few years, if there's a problem with one of the panels, it breaks for some reason, we can just put any other panel available in the market and there's no compromise on the entire efficiency of the system. So this is a micro inverter configuration. So we have used micro inverter IQ8P. So as I told you, this is actually a battery based system. I'll show you the battery when we go to the battery station. So technically this is called a AC coupling. I'm going to talk about AC and DC coupling just in a while when we go to the battery. So essentially what happens is, you can see here, these are the micro inverters. These are the micros. The same inverters have been fixed here. So the DC of the solar panels, the power produced, which is the DC power, is converted to the AC power or AC energy in this inverter. And this goes to the generation side meter, because most utility companies actually want to measure the solar generation. So we have a generation meter. From the generation meter, this comes to the battery station to charge the battery. So I will talk about the battery when we actually go down. So just a small little detail about the inverters. So these are micro inverters. So there are 8 systems. So the current characteristics of the inverters permit us to connect 7 inverters in one string. So we have got a kind of a terminal block or a termination there. We have got each of these strings. So we have made this 4 into one string, this 4 into another string. So there are 2 MCBs and there's one more main MCB. So there's a breaker there as well. And you saw there's actually a walkway here. Walkway is very important in any rooftop PV systems, because maintenance of the system is very, very important. So generally in all our projects, we actually give a walkway so that it's easy to walk and clean the panels and it's easy to inspect. So this is about the the hybrid system. It's actually called a AC coupled hybrid PV system. You can see we have also painted the surface white so that the building remains cool during summers, and also there is the reflectance, the reflected light also adds to some amount of generation, since this is a glass to glass, or sometimes called a bifacial solar PV system. So of course this is a TopCon solar PV panel. This is currently the latest technology when it comes to solar PV panels. So we have used 600 watts TopCon monoper twin peak solar panels. This is currently the latest technology when it comes to solar panels, and these are the N type. So if you have like a couple of years back, or even 1 and a half years back, they're only talking about the P type panels. So these are the N type panels. They're slightly more efficient than the earlier P type panels. So this is the rooftop layout: 8 panels, 8 inverters, elevated structure with walkway with a terminal block comprising of 3 MCBs. Now we will go down and talk about the batteries and the storage and the other electrical parameters associated with this. But this building, right behind there is one more PV setup. That's the student home. So after this, we'll go to that block and look at that student block PV system also in detail. So now let's go down and look at the battery system that we have installed here. Okay. So now we have come down. This is the battery station. So how the system here works is, the solar PV energy or the power which is generated from the rooftop first goes to a generation side meter where we record the solar output. Many of the power utility companies mandate that the power generation must be recorded. From there, the PV power comes into our controller. This is called an IQ controller through the protection. And the protection system consists of an ELCB, MCB, SPD, and a relay. And the PV system is coming into the IQ controller. So how the topology, how the configuration works is, during the day, the loads are serviced by the solar PV power. Okay, and if there is an excess power generated, it first charges the battery. And if there's a further excess power available, it is exported back to the power utility company through net metering. If we have deficit of power, we can always draw it from the power utility company, provided it is available. If the utility company does not give you power, or there's a power cut, okay, during the day, the solar PV directly services the loads without drawing anything from the battery. And during the night, if there's a power cut, we can draw power from our battery. So this is a very futuristic battery system, and this entire system actually is called AC coupling. Essentially, when we talk about energy storage when it comes to solar PV system, there are two kinds of topologies or configurations. One is an AC coupled system, other is a DC coupled system. Now, what are these AC and the DC coupled system? It is essentially how the PV system or the PV energy is interfaced with the battery. In an AC coupled system, there are triple conversions. In a DC coupled system, it's a single conversion. I will just speak to you about the AC and DC coupled system in a while, but essentially this is the topology, or this is the battery station. So let me open up these three boxes and explain each of them in detail, and also talk about the AC and the DC coupling. So let me go in detail about the power flow here. So the PV power system, with the output of the solar panels or the output from the microinverters on the top, first goes to a generation meter where we have a surge protection device and an ELCB and an MCB. It again comes into this box, the first set of protections. We have an ELCB and a 275 volts SPD here. So this PV system gets into the controller. This is the, I would say, the brain of the entire PV system. Okay, so this takes in the PV power, and this is also connected to the grid. So we have a grid input as well. So grid input also has a type 1+2 SPD plus an MCB, and the power output from here also goes through an SPD and a MCB. So these are the external protections over and above the internal protections which are already given here. So I always insist on an external protection, so that if the customer wants to isolate anything, it is accessible for him or her. So this is the brain of the system. So this takes in power from the PV system, from the grid, and it can also take the three-phase power at 63 amps if required. If one wants to monitor, it can take both single-phase and three-phase input and give a single-phase output for the backup loads. And this is our battery system. So the battery is also connected here. So again, this is called an AC battery or an AC coupled battery. I will just come to that AC kind of configuration. So the battery system here. So this is the DC side of the battery. As I told you, this is an AC coupled system. AC coupled system has actually two sets of inverters. One is what we call as a PV inverters, which we saw on the top. And there is another set of inverters called the battery inverters. So how does this system, how does the power flow happen? The AC output from the PV panel is again converted to DC to charge our battery. And the battery output, the DC, is converted to AC to service the loads. So there is a conversion here. There is AC to DC and DC to AC conversion which happens here. So this, in my opinion, is a very, very futuristic kind of a configuration when it comes to the PV power systems. So why do I say that? See, now this is a lithium ferrophosphate battery. This is actually has almost geothermal runaway. That is, it's very, very safe in terms of the thermal parameters. It is non-toxic, non-combustible, very, very safe kind of a energy storage system. This does not involve any cobalt or nickel or those kind of materials which are considered to be not so environment friendly. So that is about the battery, and this is actually a battery which can store 5 kilowatt hours or 5 units of energy. So we can actually connect multiple of these batteries to the same controller. In this site, we have only one battery. In the next site, I will show you how we have connected multiple batteries to the same controller. And one of the advantages in this kind of a topology, what we call an AC coupling, is this another set of inverters. It's actually the same inverters, the same IQ8P inverter. There are 6 of them which are mounted here. So now even these inverters now contribute for the energy output. So during the daytime, we have got the output from the PV power system, which is giving roughly about 8 microinverters into each of 480 watts. And even these 6 inverters contribute to the power output. So during the daytime, when there is enough sunlight available, our output from this entire system is the sum total of the output from the PV system plus the battery system. So this is a 3.84 kilowatt battery at 5 units. So in an AC coupled system, we have the output from the battery inverter as well. So the daytime backup loads can be the total of the PV system. We can actually connect, I think, about 15 micros to the L1 plus 6 micros which are integrated into the battery. So battery always contributes about 3.84 kilowatt of power if required. So that's an AC coupled kind of a configuration. Now I will open up this front deck further and give you a brief about the wiring and the other kind of input and output system coming from here. So before I open it, one additional feature here is a cellular modem. So this actually will require data or the internet to monitor the system. So in case the internet of the premises fail, we also have a cellular modem. So this can give us 5 years of data. It is integrated into the controller. I'll open up the front deck and give you a brief about the wiring inside. So now we have come to the IQ controller. This is actually, as I told you, this forms the brain of the system. So this has some protections. Basically, there's one relay. We have given an additional relay. This is a single phase system, but this controller can actually take 3-phase input from both from the PV side and from the grid side and give a single phase output for the backup loads. This is our gateway. This helps in monitoring the system. We can monitor the production. We can monitor the consumption. We can also monitor the grid parameters if required. And any kind of remote troubleshooting or firmware update can be done with this gateway. Of course, there is, other than the protections given here, there is a battery MCB. There is a MCB for the PV side as well. There are 2 relays, as I told you. This can take the grid input. It can take the PV input and can also give the backup power to our backed up loads. So in this ashram, we have actually connected certain single phase load as the backup. We have connected 2 refrigerators, all lights, all the fans, the computer and the TV. We have left out the air conditioner and the geyser. So all the rest are actually connected to the PV system. So the advantage or the benefit to the consumer is there's almost zero electricity bill because it's under net metering. Any excess energy can go back into the grid, and all the critical appliances are powered all the time with the help of our battery system. So there is an uninterrupted good quality power 24/7. So this is our IQ controller and the battery. So this controller can be connected to 63 amps of grid input and can also be connected to 4 batteries like this. In this side, we have got only 1 battery. We can connect 3 more if required. In the next slide, we will show you the 4 battery kind of a configuration. So this is the AC coupled system in the ashram. In the next block in the same ashram, we are talking about the DC coupled system where the DC of the PV is directly connected to the DC of the battery. So this is about the AC coupled system here. So thank you very much. So now we come to the second building or second part of the system here. This is a 4.2 kilowatt hybrid PV system. This is actually an old system. This was installed in 2019. Actually, there's a video being made here already. So we are going to talk again about the system. So that one at my back, that is one which actually we just saw. That is a on-grid, the AC coupled hybrid PV system using N-phase microinverters and the N-phase AC battery. This is now what we are standing here is a DC coupled system. You can see there's actually an old panel. This is a much smaller panel. Okay, so this is 12 panels making up a 4.2 kilowatt system. That's a 8 panels making a 4.8 kilowatt DC system. So this is a DC coupled system. That is, the PV system is directly interfaced with the DC of the battery. So here also it's under net metering. That is, the excess power can go back to the grid and any deficient power can be taken. And there is a battery system which can power the critical applications as and when required. During the day, of course, the solar PV system takes care of the load. During the night, the batteries support the critical application. So this is 12 panels. Again, we have provided a walkway for easy access and cleaning. So this is actually a string configuration. Unlike a microinverter configuration, this is a string configuration. So there are 12 panels made into 4 strings. So the drawback of a string configuration is each of these panels are dependent on each other. If there is shadow on one of these panels, so these 3 strings, the efficiency is compromised. Say one panel breaks for some reason. So then we have we can't replace any other panel available in the market. We have to choose the panel with the same electrical characteristics. Of course, these are 6-year-old panels. These are all mono panels, that is the monocrystalline panels. And since there are 12, each of these 3 is made into a string. So totally we have got 4 strings here, and 4 strings is combined into a combiner box there. That's a DC combiner box that has fuses both on the positive and the negative side. So this is a positive side fuse. We have a negative side fuse. We have a 200 volts SPD. We are given extra fuses for maintenance, and there is a DC MCB. Okay, so this is the layout and this is the panel configuration. The inverters and the batteries are down. We will just go down now and see the inverter setup and the battery setup. So this is the second part of the system. So we'll just move down and see the the inverter setup and the battery setup. So we saw the solar panels on the top. As I told you, this is the student home. So about 35 students stay here. So the PV system, the inverter and the battery system is housed here. So this is actually one of the classrooms. You can actually see the class actually going on here. So we have actually disturbing them in one way. But this classroom is actually powered from the same solar PV system. So this is a DC coupled system. Like unlike the AC coupled system we saw a little while back, this is a DC coupled system. So here the solar PV system, that is the panel DC, is directly connected to the DC of the battery. So this is our battery here. This is also an LFP battery. This is at 46 volts, 175Ah battery, lithium ferrophosphate battery from a company called Newnham. This is even more sustainable in a way because actually this is a repurposed battery from the EV car. So this is, as I told you, a DC coupled system. So the PV system, the solar panels are combined in the combiner box, which you saw on the rooftop. This is a charge controller. This is called a VT80 charge controller. It's a company called Studer. So from the charge controller, the power is actually, rather the charge controller is connected to the battery through a fuse box. And the battery is also connected to the inverter through the fuse box. This is for the protection. And the AC input and the AC output from the grid is through that box. AC output from the inverter goes to SPD, and again one more SPD. SPD means a surge protection device, and there's other protections, and this goes into the load. And this is also under net metering. In the event that we have more energy or we produce more power than our consumption, we can give the power back into the power utility grid through net metering. So the topology is the same. The solar PV panels first services the loads. If there's excess power, it charges the battery, and there is further excess, the power goes back into the utility grid through net metering. So this is again a 4 kilowatt inverter. Unlike an AC coupled system, the DC coupled system, the net output is limited to the one inverter. This is called the battery inverter. So it's only one inverter So our net output cannot be more than 4 kilowatt in this kind of a configuration. So of course, this is since it's a LFP battery, we need a CAN communication. So this is XCOM CAN. This is for the CAN communication protocol. We have a IoT device that is to monitor the batteries. The health of the battery can be monitored through that IoT device. And of course, this is our entire setup. This is a 4.2 kilowatt solar DC system, 4 kilowatt inverter, 150 volt 80 amperes charge controller, and a 8 units battery powering this student home. So this is the DC coupled system in the student home. From here, we move to the next building in the same campus, that's a Cowshed or a Goshala, where you have a similar setup. We'll just move in there. So now we have come to the third building or the third part of this project. And in my opinion, this is the critical part of the critical phase or the critical aspect of this project. This is the Goshala. Of course, here we have the smallest PV system here, just a 2.4 kilowatt PV system. But this Goshala or this Cowshed is extremely critical because this is the Goshala which is actually supplying the cow dung for our biogas plant. As I told you, this campus has about 40 students and about 6 to 7 support staff. And there's enough cooking requirement. So Goshala provides daily cow dung, which we dose into the biogas plant, from which at least 2 meals in a day is cooked by the fuel supplied by this Goshala. And the beauty is this Goshala is again powered by the solar PV system, a DC coupled hybrid PV system. Goshala, there's nothing like critical or non-critical loads here because Goshala only has about some few lights and some fans and a TV for the support staff here. So all the loads are serviced only by this solar PV system. So Goshala is right behind me. This is the staff quarters. We have got 2.4 kilowatt hybrid system, again using TopCon solar PV panels. We have mounted the panels on the rooftop. So these panels are connected to the battery and the inverter. So we here come to the battery station here. This is the battery station for the Cowshed or the Goshala. So the 4 panels are made into 2 strings, and there's a DC combiner box. We have got 4 fuses, a 200 volt SPD and a MCB. And we have a charge control. This is called a VT60, 60 amperes, 150 volt charger. The charger is connected to our battery. This is again lithium ferrophosphate battery, 51 volts, 100 Ah battery from Unum. Again, this is LFP batteries at 5 units. In my opinion, very sustainable since it is a repurposed battery from a EV car. And the same battery is connected to the inverter again through a isolator. We have got 2 DC switches as isolator, and we have a DC box. So the inverter this is an AC box. The inverter can take AC input, can deliver good quality AC output. So both the AC input and the output are protected through ELCBs, MCBs and SPDs. And this power is injected into the loads of our Goshala. And any excess energy first charges the battery. Further excess goes back into the power utility grid under net metering. So this is also a DC coupled system. So DC of the panel is directly connected to the DC of the battery. So this is about the solar PV systems that we have installed in our Ramakrishna Yoga Ashrama. The AC coupled hybrid system in the main Sanctorum. We have a DC coupled 4.2 kilowatt system at the student home. And we have a 2.4 kilowatt solar PV system. All of them, of course, LFP batteries. And this makes the 3 solar components in this project. From here, we move on to a biogas unit, which we have installed right behind the kitchen, which is providing good quality cooking fuel for our campus. So let's move in there. So now we have come to the biogas plant at our Ramakrishna Yoga Ashrama. So this is actually my personal favorite, one of the best nature-based solutions for energy requirements. And in my opinion, this takes the minimum environment footprint to build it. That is, the cost of environment in terms of building this infrastructure is very less. So I have earlier spoken about biogas plants. Mostly I have shown the floating dome kind of a biogas plant. This is slightly different. This is a fixed dome. This is the dome of the biogas plant. This is a fixed dome. The dome doesn't move here. Unlike the rooftop biogas plants where the dome moves, and as and when we actually feed in and as when the gas is generated. This is a fixed dome. This is more suitable for higher feed and higher pressure and higher requirement of gas. So the concept is the same. Basically the household or the organic waste here is fed into the digester. The digestion happens, methane is produced. The methane is scrubbed and taken into the kitchen for cooking gas. This is slightly more elaborate compared to a rooftop scale floating dome kind of a biogas plant. This is a fixed dome. I'll just walk you through the components in this and how this actually works. So it starts from our mixing tank. This is the mixing tank. This is where the organic waste is mixed with water. We have provided a water line here. So the water comes here. So you can put in your waste and mix the waste here. We'll have to properly mix the waste before dosing in. So a water line is given so that the waste can be put here and mixed. So this is designed to take about 80 kgs of waste per day. 80 kgs means 40 kgs of solid, rather the organic waste mixed with 40 kgs or 40 liters of water. So totally 80 kgs of feed can be given into this digester. So this is the mixing tank. The maximum solid waste which comes here is the cow dung from our Goshala. We can also mix the organic waste from the kitchen, that is the leftover food, peels, vegetable waste, fruit waste, etc. So all our waste can actually go into the mixing tank. This is the mixing tank. So the waste is nicely mixed here with water, and from here, after mixing, it goes into our feeder tank. This is the feeder tank. I have provided a valve here. Once the waste is properly mixed, we can open the valve. Of course, it's important to mix it with enough water. So now we'll open the valve. Now the waste starts going, rather the slurry, the input starts going into the feeder tank. This is the feeder tank. So all the waste is given into the feeder tank. From the feeder tank, the input comes into our digester. So this is the digester. This is the main component of the system. So this is where an anaerobic digestion process happens. This is deliberately painted black so that the surface is warm or hot. Higher the temperature, better is the digestion. So anaerobic reaction happens here, which converts our waste into usable methane. The gas so produced flows in this pipe into the kitchen. So this pipe, you can see there's a small detail here. The gas goes like this and there's elevation given deliberately. Sometimes there will be moisture or some water in the gas that has to be taken out from time to time. So in that kind of a scenario, we can open the valve here. The moisture release valve is given, which takes out the moisture from the gas. So this gas now goes into the kitchen. And now we come here to the slurry tank. This is called a slurry tank. So in the digestion process, a byproduct is a very rich liquid, undigested liquid. So this is the tank. This is deliberately made little bigger so that if there is a deficiency in the feed, whatever is the slurry which comes out here can go back into the digester. So this slurry gets accumulated in this tank, and when this tank overflows, this goes into an overflow tank here. So this is the usable slurry. So this is very, very rich in NPK content, and this can be used for our farm. As you can see, we have a pretty decent and pretty big farm here. So this slurry here is mixed with water, and that is dosed to our plants. But one has to be careful, it cannot be put directly. For smaller plants, we recommend 1:5 dilution. For bigger plants, 1:3 dilution. So this is the usable slurry, and this is a slurry tank where the slurry gets collected. Only the overflow goes there. Okay. And now the gas which is so produced contains some amount of impurities, mostly hydrogen sulfide, moisture, and carbon dioxide. So we have given a small scrubber or a filter here. There is a 3-stage filter. So the gas so produced first goes into a cartridge with water where some amount of carbon dioxide is dissolved. Then we have a desiccant which has a activated carbon. So this removes moisture from the gas. Further, the gas moves into a chamber with steel mesh which scrubs some amount of hydrogen sulfide. So the gas which goes from this scrubber or filter goes into our kitchen. So we have our kitchen here. So enough and more gas, almost 3 to 4 hours of gas per day is produced. It's enough for about 2 meals in a day. The kitchen is right inside. We will go inside and see our stove and the cooking process. So this is our kitchen now. So we have the biogas digester right there. So the fuel is made right there. The biogas is generated right there. After scrubbing, we have connected into the 2 stoves here. So one is here. This is called a canteen burner. So this is a bigger burner, right? So here, this is generally used for cooking higher volumes of stuff here. So this is a canteen burner. The gas is connected here. We also have one more burner here. So this is a hybrid stove. I have spoken about hybrid stove earlier. This has got 2 burners. One side is the biogas. You can see a slightly bigger diameter of the hose there. This side is our LPG. So the biogas is now connected to both the stoves. For roughly about 40 people here, 2 meals in a day is cooked using our biogas. So that's about the biogas. Why I say it's so beautiful is the fuel or the cooking gas is produced right behind the kitchen. So the environment footprint of this gas is almost nil or negligible, or to say it's rather very, very minimum. This is about the biogas digester in our campus. Thank you so much.